Okay, so last time we stopped on this slide. I believe we were talking about. I think we explained this equation, and we said how this equation sort of in a Ohm's law sort of format. So voltage times the admittance instead of divided by the impedance. The voltage times the admittance is equal to the current. So we said that basically this would be the corresponding magnetizing inductance representation, since basically the difference between the two currents, the primary and the secondary ampere turns, or the primary and secondary magnetomotive force, is basically the magnetizing component of the current. So we were able to say, we concluded that we can call the value of susceptance, which is the complex component of the admittance, which in this case is the parallel magnetizing branch. The value of that will be the reluctance over omega times the number of turns on the primary squared, right? And we saw that this current component, since it is the current component that is lagging this voltage E1 by 90 degrees, according to this minus J value here, this will be in phase with the flux that it is producing, right? So it's producing this flux, and it is in phase with this flux that it is producing it. And that's what we have on the phasor diagram here. And then we said that we have something else that we didn't represent in the equivalent circuit of the transformer, which is the actual power losses in the core. So the core has eddy current losses, has hysteresis losses that we need to represent. These are real power losses. They're not reactive power that is required to set up a magnetic field. It's not flux that is going to be set up and then collapse, set up and collapse. Because you're setting up this flux and collapsing it, you have some corresponding power that is being lost in the core due to eddy current and hysteresis, right? So we have to represent that somehow. And this component is also present whether or not you have a load on the secondary side, because it depends on having the flux in the core, right? So if you have time varying flux in the core, you will have eddy current losses and hysteresis losses, right? So because you have that, then it's also a parallel branch. It's not a series component. It's a parallel branch. It will always exist. Anytime you have voltage being created, it will have to exist with the voltage that's being created, right? So that's why we will represent it as a parallel branch as well. So we will say that this component of current, which is corresponding to the core losses, will be is the result of the voltage being generated in the core, and it will have a value of this voltage divided by some value of resistance I R core. This value of resistance R core is going to be defined by basically the value of current IC. So this current will be drawn. So you will have, as soon as you apply a voltage, there will be current drawn to magnetize the core of the transformer. As well, there will be a component of that that will be used to compensate, or that will be used as a power loss burning component, or a power loss component in the core of the transformer. So if you take that voltage and that current and divide them by each other, you will be able to find the value of that core loss component, which is RC that we have, that we will add to the equivalent circuit. Okay, so E we will know from the E equals n d phi by dt. That's just the voltage created by the flux linkage. And then the IC will be additional current that is drawn in addition to the magnetizing current that will be due to or that we will use to represent a resistive component. There is no resistance in there, right? We found that there's an additional amount of current being drawn, and this amount of current is actually in phase with the voltage. And we said, okay, if it's current in phase with the voltage, and it's due to the fact that I will have a voltage generated, it's required for me to generate that voltage, then I will call it the core loss component. So it's sort of representing everything due to the hysteresis and eddy current, or the real power losses in the transformer, not the reactive component, the reactive power that's available in the transformer. So hence we have two components of current, magnetizing current, and the core loss component of current that exist when transformer action happens, right? So whether or not you have a load on the secondary side, it's independent of that, right? As long as you have transformer function happening, meaning ampere turn on the primary, ampere turn on the secondary, there's a difference between them, meaning you have flux flowing in the core. As long as you have flux flowing in the core, there will be something called excitation current, I0. This excitation current will have a reactive component, which is the magnetizing current, which is due to the flux being set up in the core. Because we have flux being set up in the core, we have eddy currents and hysteresis losses, which are real power losses. These we represent as a resistance because we take this component, this value of component current, which is the excitation current, and divided it up into two components that are 90 degrees from each other. One is in phase with the flux, and this is what produces the flux. One is in phase with the voltage, and this is a resistive loss that accounts for the additional real power losses in the transformer core. Okay? And this excitation current is typically at full rated load, is typically about less than 5% of the current. Right? So it's less than 5% of the rated current of the transformer, typically. Okay, so we can rewrite this excitation current as a summation of the core loss component and the magnetizing component of currents. And then that is equal to the voltage times the admittance. Admittance is parallel branch admittance. Right? Any questions on this? So now we can draw this parallel branch. Right? So if I take now this voltage, E1, divided by this admittance, then I can get the current, the excitation current. Or if I have the excitation current, and I should be able to, from the knowledge of these components, find the voltage or vice versa. It's basically a circuits problem now, right? So I think we try to account for all the components in the equivalent circuit. Does anybody have questions on any of the components? So now that you have all these components, we think it's too complex, so we will simplify it. Right? So we will leave the details of all these components and how to deal with them in 338, and then here we will simplify. So we will do some simplifications to this circuit by using, by doing this, the impedance, transferring the impedances from primary to secondary. We will sort of, using the knowledge that we talked about last class, meaning the idea of being able to transfer the value of this impedance here to the primary or all of these impedances to secondary, we will sort of simplify and see what the transformer will look like in a power system from a power systems perspective. What's interesting for us to do here, okay? So what's interesting for us to do is, okay, let's start by ignoring this excitation branch, right? Even though we spent a lot of time explaining it, so we will ignore it. So typically you will not see it, in any power flow problem or any power system design problem, you will not really see that. You will see it when you sort of talk about the transformer specifically, like we did for a while, we talked about transformer, so this was important for us. But from a power systems perspective, I don't care. It's less than 5% of rated current. So I will typically ignore this branch. And then I can bring the secondary impedance to the primary by multiplying by the turns ratio squared, right? So the secondary X, the R and X on the secondary, I can multiply them by the turns ratio squared and bring them to the primary side, right? So I bring everything to the primary side. I ignore this branch. So I basically have a single impedance on the primary side. Again, if your transformer is designed properly, right, you're not going to design it with a huge power loss. You will make sure that you've selected your conductors such that the resistance of these conductors is as small as possible, especially these large power transformers. Again, if you're processing 100 megavolt amperes, right, even 1% of loss is big, right? So it's 100 megavolt amperes, 1% is 1 megavolt ampere, right? So it's almost 1 megawatt if you assume unity power factor of loss. Right, so what will that do to the temperature of the transformer? It will raise it like crazy, right? So you cannot live with such losses yet. So you will have to typically design your system, your transformer, such that you minimize the value of the resistance considerably. So in power systems, especially on the transmission side, Distribution side, we are sometimes, again, we are crammed on space. We don't have space in the building, we don't have space. So the distribution transformers may be smaller. Smaller transformers mean smaller wire, mean higher resistance, mean higher losses, right? So a lot of what we're talking about is very applicable to the transmission side, higher voltage side. So we will typically also ignore this value of resistance. Fine, you will see some problems where it's included, but typically we will ignore it. So we end up with what? Basically, we're representing the transformer in a power system as nothing but a series reactance. So it's nothing but a reactance. And what is this? What is this now? The ideal transformer. This is nothing but the turns ratio stuff that we talked about. Nothing but the gearbox, right? VI equals VI, right? So VI in the primary is equal to VI in the secondary. So the transformer will typically be represented as that. And we will take this a further step today. And we will also figure out a way to eliminate this somehow. So we will look at that. We will see how to do that next, right? So we will end up with a transformer being nothing but a series impedance, right? If it's a series impedance, go back to your single-phase equivalent circuit. Nothing but a series impedance, right? Just a series impedance in your single-phase 214-like equivalent circuit, right? So we will see how to do that. But for now, we still have the ideal transformer in the middle, and we have basically reactance, series reactance. Okay. So we'll go through this quickly. I think it's not one of our core interests, but if you want, when you buy a transformer, you will have to, of course, test this transformer. So I think you do this experiment in 338, and you find the parameters of these equivalent circuits, right? So if you want to buy a transformer and you want to test and make sure it's working properly or has the proper parameters, you need to figure out a way to test it. So we test the transformers and calculate its parameters or estimate its parameters. Estimate its parameters is a better word, using two tests called the short circuit and open circuit test. So let's think of this. If I have this transformer here, if I have this big transformer here, okay, with this parallel branch included, okay, if I place a short circuit on one side, right, and I put a voltage source on the primary side, and I apply full voltage, right? What am I going to get? What's going to happen to the transformer? What value of current am I going to get actually? Will it be rated current? Rated means you have equipment that is rated for 100 megavolt amperes, meaning typically rated resembles the fact that the transformer is able to dissipate the amount of heat without raising its temperature too much, right? So your power supply is rated for a certain power, right? When in 438 you bought switches rated for a certain value, right? But what if you cooled the switches? Can you increase the amount of current that's going through them or not? Yes. When I was working at Schlumberger designing downhole tools, right, we would buy switches used for, people don't manufacture switches for Schlumberger, right? They manufacture switches for the market, right? So you buy electronics for whatever is used in the market, but instead of running it at 100 amps, we run it at half an amp. We run it at half an amp, and we try to put the best heat sinking available, put the best thermal grease, and make sure that we couple the board to the outside, and we do as much as we can to make sure that we dissipate the heat, right? So typically power devices or electrical devices are rated based on how much heat that they can withstand, really. I mean, fine, insulation breakdown is another consideration, right? But so basic two considerations: insulation breakdown or physics, right? And then heat. But heat is really the major thing, right? So if you put a short circuit here and you put full voltage, do you expect to see rated current, meaning normal rated value of current, or something a lot higher than that? If I put full voltage here and I put a short circuit, I would expect to see something a lot higher. If I put a short circuit and I start ramping up the voltage slowly, right, then at some point I will reach rated current. Right? But typically when you put full voltage, you're expecting to have a certain load, and this load will have a certain impedance that is not going to draw a short circuit current, right? if you have a short circuit, it means there's a fault of some sort, right? In a power system, when a transformer when it's operating. So what we do is we don't want to generate short circuit current as such. We don't want to generate something above the rated current, right? What we want to do is we want to generate rated current. Why do we want to generate rated current? Because we want to have, so we place a short circuit here, and we put a voltage source here that we raise its value slowly until we reach rated current. If we reach rated current, what is this excitation current with respect to rated current? Is it important? Is it considerable? We said it's not very considerable, right? So what's going to happen is if I put a voltage source here, that I raise slowly, and I put a short circuit, then I would be able to push rated current in the transformer. If I push rated current in the transformer, then I put a voltage, rated current will flow. This current will flow through this impedance, the series impedance, right? Because I have rated current flowing, I can sort of ignore my excitation branch. It's a very small amount of current anyway. When rated current is flowing, it's a small amount of current. So since it's a small amount of current, okay, it's like ignoring this parallel branch completely. In that case, it's like having a voltage source placed here and nothing but these series impedances with a short circuit here, right? You know, you find a short circuit, you transform it to this side, is also a short circuit, right? So it's like supplying a voltage source across these two impedances. So what does this mean? It means that if I measure the current coming into the circuit and I know my voltage, I can know my impedance, right? I can calculate this series impedance, which is the transformer series impedance, right? So I've been able to identify that. So using the short circuit test. How about if I do the same thing, but instead of, do something similar. So instead of putting a short circuit, I keep it as an open circuit. What happens?
No current will flow.
No current is going to flow to the secondary, meaning no current will flow into this ideal transformer stage, meaning the amount of current that's flowing here is minimal, right? So the current that will flow mainly will be what? The excitation branch. There is some error, of course, because there is a primary resistance that the current will flow through, and then as well as the leakage inductance on the primary, right? So there is some error to this, right? But the majority of the current, the significant portion of the current, will actually be due to the excitation branch, right? So then, if that's the case, if I also measure my voltage, measure my current, then I should be able to tell you, okay, this is my excitation branch impedance, right? Okay, so do I do that on the primary side and the secondary side? Let's look at the open circuit test. If this is a step-down transformer, high voltage side, low voltage side, okay, where would you want to perform your, so high voltage side is high voltage, low current. Low voltage side is low voltage, high current. So to do the short circuit test, I think it's better to maybe use a lower voltage source and have lower short circuit current, right? If I put this is high voltage, high current, low voltage, high voltage, low current, low voltage, high current, right? So if I put my voltage source, if I want to buy a voltage source to conduct a short circuit test, it's easier to buy a low voltage source, right? So I would put my voltage source on the secondary side, and then place a short circuit on the primary side because it has less current, right? So that's you can do it either way. It does not matter. You can do it on the primary side or secondary side. Just what we're talking about, what is more practical, right? What is a more practical approach, and that's what they have here. So here they have, okay, this short circuit test, or they're conducting the short circuit test, and they say, okay, for the short circuit test, I want to have current flow, right? Yeah, for the short circuit test, they're doing it from the primary. So short circuit test, you put the short circuit on the secondary side. If you put the short circuit on the secondary side, right, the amount of current flowing on the primary side is low, right? So you can buy a voltage source. So you will buy a voltage source that is rated for, but again, are you putting rated voltage? You're not putting rated voltage. So this is a low voltage source. And is it a high current voltage source? Is it going to see short circuit current, or is it's going to see rated current? The objective is to push rated current in there. But rated current on the high voltage side, is it low or high? So this is the high voltage side, will have low value of rated current. This is the low voltage side, it will have high value of rated current, right? So this is high voltage. This primary side is high voltage, low current, right? And then the secondary side is low voltage, high current, right? So to conduct the short circuit test, I can do it either in primary and secondary. I want to create a short circuit. If I put the short circuit on the primary side, and I put my source on the secondary side. If I do that, what do? What happens? I need here a source that is low voltage, fine, not full, it won't be rated voltage for sure, right? But the amount of current that I will have to push here to create a short circuit on the secondary side will be what? Remember, this is high voltage side, low current, low voltage, high current, right? So for me to push short circuit current here, meaning rated current on the primary side, on the secondary side, this rated current is the high value of current, right? So since here it's high voltage, low current, here it's low voltage, high current. So this is high value of current. So instead of getting a power supply with a high value of current, it's cheaper to conduct this test with a power supply with a low rated value of current, right? So you would conduct the short circuit test from the primary side for that purpose. But does it matter? No, it does not matter really. You can do it this side or that side, right? It does not really matter at the end of the day. But just from an economical perspective, people would do the short circuit test this way. And then the open circuit test, right? The open circuit test, what would you like to see happen? I'm not going to be pushing much current at all, right? And I need a voltage source. I need to place a voltage source either on the primary side or the secondary side. It's cheaper to get, but I need to put full voltage in this case, right? Here it was a reduced voltage. Reduced voltage. But now, to conduct my open circuit test, I need to, remember, to find this value of magnetizing branch, we came up with an equation relating what? Relating I magnetizing is equal to some value of admittance, the parallel admittance, multiplied by the voltage, right? So I need the full voltage to actually find this value of impedance here. So to conduct the open circuit test, I need to conduct it at full voltage. So it's cheaper to buy a low voltage source in that case. So I can buy a low voltage source, put it on my secondary side, which is low voltage, right? Put it on secondary side, conduct my test. If I put voltage here, again, I'm only pushing very small amount of current, right? It's only magnetizing current that's flowing, not the full current. So because this is an open circuit on this side. In this case, the current will flow through this magnetizing branch, and I have my E voltage now, or the voltage E, and I have my magnetizing current flowing as well, or excitation current flowing. Okay? So any questions on this? Yes, ma'am.
What are you trying to
I'm trying to calculate the parameters. Because if I do this, if I'm pushing rated current in the transformer, we said that the magnetizing branch is only, this magnetizing branch is only a small percentage, let's say 5%, less than 5% of rated current, right? So if it's less than 5% of rated current, I can neglect it if I'm pushing rated current. If my source is supplying rated current to the primary, then I can neglect it. So how do I supply rated current to the transformer? I put a short circuit on one side, and I put a voltage source on one side, and I ramp it up slowly. My objective is to push rated current. It's not to place rated voltage across the windings. Okay? So since that is the case, I put a low voltage source that is going to supply rated current on this side. And if I do that, then I know this voltage and I know this current, then this voltage and current are placed across this impedance. then I can calculate this impedance. And same thing with the open circuit test. With the open circuit test, if I leave the terminals open, the windings open, and I put full voltage across one side, I will see full voltage across the secondary side. Here, the primary side. If I put full voltage here, this voltage is going to be placed across this impedance. This series branch is open circuited. There's an open circuit. Fine, there is some discrepancy here because it's an estimation because I have, I have resistance on the primary windings, on the secondary windings in this case, and I have some leakage flux, right? So there is an approximation, right? But if we ignore that, then the bulk of the current is actually going to flow through the magnetizing branch. And if I take that current, divide it into its two components, I will know the magnetizing component and the core loss causing component. Hence, I can calculate, if I know the voltage and I know the current through this, I know the current through this, then I can calculate these two values, right? So the objective is to calculate the parameters. Okay, so let's see what the example says. A single-phase two-winding transformer is rated for 20 kVA, 480 volts, 120 volts. So 480 volts on the primary, 120 on the secondary, 60 hertz. During the short-circuit test, where rated current at rated frequency is applied at the 480 volt winding, to winding 1. So this is the short-circuit test. With the 120 volt winding shorted, the following readings were obtained. So the voltage was 35 volts. This voltage source was 35 volts. It's a reduced voltage. Right? They also gave us the power. Right? So during the open circuit test, where the voltage was applied to winding 2, with winding 1 open, again in the second test here, they gave us the current, and they also gave us the power. Right? We're rated, and we know that the rated voltage is applied. Right? So we know voltage, we know current, we know power. In the first one, we know voltage, we know current, we know voltage, we know power, and we know that rated current is flowing. Right? Here, rated current at rated frequency is applied. So, and since we know power, we know the 20 kVA, we know voltage, and we know current, and we know real power, we know almost everything that we can. We have a voltage source that is supplying a current that we know. It is dissipating a certain amount of power, real power that we know. So we can, after you find the current, from the knowledge of the real power, you can find your resistance. Right? So we will go through that. So basically, they give you everything that you need to find these two impedances that are in series. And then here, the second case, they give you the voltage, and they give you the current, they give you the power as well. So you can segregate also the real and reactive power losses in this case by knowledge of the real power that's in the circuit. So, okay. From the short circuit test, determine the equivalent series impedance. From the open circuit test, determine the shunt admittance. Basically, that's what we were talking about. So let's see how they are doing it. Okay, so for the short circuit test, we said that the equivalent circuit will look like this voltage source, right, with the resistance, the reactance, and nothing but the ideal transformer here, right? This is my equivalent circuit. I know my S is equal to 20 kVA, right? And I know my rated voltage of the transformer. So this is my rated power of the transformer, right? This is S, rated power. If I want to find, remember for the short circuit test, I am pushing rated current in the primary. So for me to find out what the rated current is, given the rated power and given the rated voltage of the winding, right? This is rated voltage, rated power. I should be able to calculate my rated current, right? This rated current, I need to find the voltage source value that if I put that value will flow rated current when I have a short circuit, right? This is not running. This is not the amount of power that is being transferred to the transformer. This is just the rated power, right? And my rated voltage, this is rated power, and this is rated voltage is equal to 480 volts on the primary. So from rated power, S equals V times I. as magnitudes, right? So from rated power and rated voltage, I know rated current that I want to push through the winding. So I will get a voltage source and keep ramping up the voltage until I see rated current flowing when I have a short circuit on my secondary side. When I get there, I will stop. And I will do the measurements of power. So if I do that, and I measure power, I was given power is equal to 300 watts. So I ramped up the voltage until I saw rated current flowing, and the corresponding power was 300 watts. I used the 2-watt meter method or whatever watt power measurement method, and I measured power. If you have real power flowing, that means this real power is being dissipated in this resistor, right? You only have a resistance and a reactance, right? There's nothing else. The equivalent circuit is a source, a resistance, and a reactor. This is a short circuit, basically. Right? So any real power will be dissipated in the resistor. So from I squared R, basically power is equal to I squared times R, which I'm pushing rated current through, right? So it's I squared, the rated current, times the power divided by the rated current. So that's my resistor. That's the value of the resistance. And the value of the impedance as a magnitude is nothing but the magnitude of the voltage divided by the magnitude of the current, right? Voltage divided by current is going to give you the magnitude of this impedance. So I got the magnitude of the impedance as well. I now need to extract from this magnitude of impedance my reactive element, reactive component. So I have the R, and I have my Z as a magnitude, but I don't know how much X I have at the moment. So but from Pythagorean theorem, I know that Z squared is equal to R squared plus X squared, right? So I can solve for X in this case. So given Z, which is here as a magnitude, and given R as a magnitude, I should be able to solve for my reactance, X. Yes? Okay?
Can we use complex power to find the angle?
But you don't have the value of reactive power. Right? You don't have the value of reactive power. I mean, you can conduct a test to measure reactive power instead of active power, right? If you conduct a test to measure active and reactive power, this problem can be given in a different way, right? I can tell you, okay, I measure, and during the short circuit test, this is the rating of the transformer. I measure certain reactive power, a certain active power. So from the active power, from some P divided by I squared, you will get R. And Q divided by I squared, you will get X. Right? Instead of going through this is another way to pose the same problem, right? If I measure active and reactive power at the input, so I can do that. Yeah. Okay, so this is the short circuit test, and from there I was able to find the series values of the impedances that I have. Now for the shunt branch. For the shunt branch, I need to apply full voltage, right? I need to apply full voltage on, is it easier to apply it secondary or primary side? Secondary because it's lower voltage, right? So I apply full voltage on the secondary side. This will be transferred to the primary side using the turns ratio. I have an ideal transformer. I put V on the secondary, some voltage on the secondary side. It will be ramped up by the turns ratio on the primary side. Take that voltage divided by, place it across that impedance, some current will flow. They gave us the value of power in that case, and we know voltage, right? Did they give us anything else? That's it, I think. They just gave us power and voltage. So if I know real power, I'm placing this voltage across an impedance. This impedance is a combination of an R and an inductance. If I know real power, this real power is being dissipated only in the resistance, right? I know that for a fact. So given the voltage on the secondary side, it's the rated voltage, but I transferred it to the primary side. So this is my E2 voltage, is my voltage on the secondary side, which was 120 volts. I transferred it to the primary side, which is from the turns ratio, it will be 480 volts, right? So if I'm placing full rated voltage, then it's supposed to be 480 volts on the primary side, right? So that's the voltage that now I have across my shunt branch. I take that voltage I know that voltage, and I know the power that is being consumed when I ran that test. The real power that is being consumed when I ran that test was 200 watts. So real power divided by the voltage squared, I should be able to get the conductance portion of the admittance, right? Admittance is divided by conductance and susceptance, right? So the real power is dissipated in the conductance, right? So I was able to calculate my conductance, the resistive branch, and we go through the same process, right? So if I know my my conductance, and I know what else. So how do I calculate the admittance? Yeah, so the conductance was only a portion of that power, the portion of that impedance that is consuming that real power. Now, if I take my voltage divided by that, my voltage and current, so I have my current. Remember, I have current as well. Remember, I have excitation current. I think they told us how much current is flowing. Yes, they told us 12 current is flowing. 12 amps is flowing. So 12 amps is flowing, and 200 watts has been dissipated. So if I know from the 200 watts, I was able to calculate the real portion of the impedance, right? So I was able to calculate this one. I know this voltage. This voltage is placed here across this impedance. So voltage squared divided by the impedance, or voltage squared multiplied by the admittance, right, is going to give us this value here, right? Power is equal to voltage squared divided by the value of the impedance, right? Or voltage squared times the admittance, right? So from power and voltage, I was able to calculate the real component, right? And now from voltage and current, right? From the voltage and current magnitudes that I have, I should be able to calculate the magnitude of the full admittance. I know the real part, I know the magnitude, exactly like we did for the impedance. I know the real part, I know the magnitude of the impedance. I was able to calculate the reactive component. Same thing here. I know the real part, and I know the magnitude of the admittance. I will be able to divide it up into the real and imaginary parts as well. Okay? Same process, exact same process. So the real part from the real power. The magnitude just from the voltage and current that you're given. The magnitude of the admittance. And then when you know the real component and the magnitude of the admittance, you should be able to calculate the complex component of the admittance in this case. Any questions? Yes? No? No? No, why? Do you have any problems? No, seriously. You're okay? Okay, so not that the equivalent series admittance is usually elevated. Anyway, so this is the summary of this evaluation of the short circuit. Why we put short circuit current in there, and why we put full voltage in there. So mainly we put full voltage in there because when we go back to here, when we went back to this equation, I needed full voltage to be able to calculate this shunt branch, the reluctance, the value of this impedance, which is my shunt impedance, which is depending on the reluctance and the turns ratio squared, requires the actual full voltage to be able to calculate it. So that's why in the open circuit test I use full voltage here. But the series components, they're not really used for creating the voltage. They're just losses on the way. So I just need to push rated current in there to be able to calculate them, right? So that's the justification behind what we did to calculate the parameters of the transformer. Okay, so they do this. Do they do this really in real life with the transformers? Yes, they do. Okay, so it's when you go and buy a transformer. When you go and buy a transformer, I know people at Rasgas when you go and buy, you will go to the factory, and one of the factory acceptance tests that you will conduct is to measure the parameters of the transformer to make sure that it's what you're expecting. Why? We will see later, because again, this is going to be now part of our single-phase equivalent circuit. It's an impedance in our single-phase equivalent circuit. If it's too much impedance, too much reactive power that's going to be required to do this transformer action, I don't want it, right? So it's a component. It's something in our circuit that we need to account for. It cannot have more impedance than what we expect or less impedance than we expect. It should be exactly what we expect. So now that we've talked about the equivalent circuit with all the with some non-ideal parts of the circuit, did we consider everything? No, we did not consider everything, right? So this equivalent circuit does not consider saturation. Saturation is when what? So you're in your BH curve. In your BH curve here, we assume that B is equal to mu H, right? We assume that it's a linear relationship, right? We also never assume that the transformer material will saturate. We just said, okay, we put B, we multiply by mu, we get H. H is the magnetomotive force, right? So the magnetomotive force required will depend on mu, and it will set up a certain flux in the air gap, right? We assume that anytime I put more current, I will get more B. Current is proportional to H, right? Current, the H is the magnetic field intensity is equal to N times I, right? It's the N times magnetizing current, right? So basically it's proportional to the current. So if I put more current, I will get more flux. And this is not true, because at some point your BH curve starts saturating, right? So you put more current, this is H, more current, you will not get more B. If you put more current and you don't get more B, then there will be no time varying flux component in that case. If there's no time varying flux, then there's no additional voltage generated across the windings to allow you to overcome higher currents coming into the transformer, right? So this is one non-ideality we did not consider in the model, right? And this will cause, during operation, if you put a higher voltage or if you're pushing a higher current in the transformer than you're allowed to, then you will find that current that you're putting in will not be contributing to additional voltage across the winding, and you're just burning power. This is during operation, right? So something to consider. We did not look at that in the equivalent circuit. Another thing to consider is related to what we just talked about. If you're on the BH curve and you're at that top here, at this knee here, remember, magnetic materials have some residual magnetization, right? So if you magnetize a magnetic material and you remove current, there will be some residual magnetism left in the material, right? So the next time you energize the material or next time you run the transformer, you're not necessarily starting from B equals 0 in the core. There may be some residual flux, like a magnet, right? Magnets have some residual flux. If you remember in 322, the coercive force or something, I don't know I'm not sure what it's called, but there is some residual magnetism in the magnet, right? After you magnetize it, it is not demagnetized, right? It will maintain its magnetism. Similarly, the magnetic lamination materials are similar, very similar. Fine, they don't maintain a very high value of magnetization, but there is some residual magnetism. If there is some residual magnetism and you run the transformer, initially there is no back EMF as well generated across the windings. But if you're starting from zero, if you're starting from the zero magnetization, you have all of this to go up, to climb, right? But let's say, so when you put voltage, which will lead to current, you'll be climbing the BH curve, right? But what if you had some residual magnetization and your magnetization in the core was up here, for example? What will happen? You put voltage, which will push current. You'll try to push up this magnetization curve and then back down. When you're pushing up here, the variation in flux is not much. So you're not going to be generating a lot of voltage initially, right? So you will have a huge inrush current at the beginning, like the motor starting, like induction motor starting, something similar. Very high peak currents for a few cycles, and then it will decay down, right? So this is called inrush current. So we don't consider that in the equivalent circuit as well. Non-sinusoidal exciting current is due to the fact that the BH curve is not linear. So our assumption was B equals mu H. What does this mean? It means that, let's look at this. It means that if I have a certain flux linkage, right? If I have a certain flux linkage, let's say this green now is smaller than these two lines, okay? If this green sine wave is smaller than these two lines, then if I take any point on this green wave, multiply by this linear relationship between mu and h, right? I will get also what? I will get a sinusoidal waveform, right? B equals mu h. Which h is what? H is the magnetomotive force required to create this excitation or the flux in the air in the core, right? Right. If we go back to our N1 minus N1I1 minus N2I2, the difference between them is this magnetizing current. This magnetizing current is basically the magnetomotive force, the amount of voltage in an electrical circuit required to push current, which is flux, in the core of the transformer, right? If they are directly related by a linear relationship, B equals mu h, then I take B, which is a sine wave, right? Remember, my flux is a sine wave, my voltage is a sine wave, my flux is a sine wave. Remember, the voltage and flux are related by differentiation. E equals n d phi by dt. So if my voltage is a sine wave, this is a sine wave, but phase shifted with respect to it. It's a sine wave. So I took my flux now, I said it's equal to mu h, right? If it's only equal to mu h, that means there's a linear relationship between the flux linkage and the excitation current, which is due to the magnetomotive force, right? Which is this h that I have, right? So if I take a sine wave multiplied by something linear, I will get what? A sine wave, right? I take a sine wave multiplied by this linear relationship that is governing this sine wave, right? B equals mu h. B equals mu h. This is B, right? And this is sort of proportional to h, right? So if this B was here, right? What I'm doing, which means I'm in this linear zone. Linear zone means I'm complying with this equation. This is B, and this is h. This is the axis for B, and this is the axis for h, right? In this zone, between these 2 points, B equals mu h. It's a linear relationship between B and h, right? In this zone, if I take every point, every value of B, multiplied by a value of mu, and I plot it here, take this, put it here, plot it here, take this, put it here, plot it here, I will get some sine wave, right? It will just be scaled. It's a scaled sine wave, depending on the slope, or the relationship between mu and h is depending on the slope of mu, right, in this case. But if this mu, the relationship between B and h, is not linear, which is what we have here. What we have here is the relationship is not really linear. So what will happen is if you take this point here, put it here, you will get something way up here, right? If you take these points at the top here, they will be transposed into these peaky currents. You will not be creating a nice sine wave. You will be creating these peaky waves, right? So what does this mean? What does this mean in terms of power quality? Is this a pure sine? It's not. Then it has harmonics, right? Anytime if it's not a sine, then it has harmonics, right? So then excitation current of the transformer will have harmonics. So you have to make sure you will deal with that. Is it acceptable or not? Sometimes harmonic content in a power system is not acceptable, right? It may correspond to the resonant frequency of your generator, and hence you're supplying a certain value of voltage or current at the resonant frequency of an electrical circuit. What will happen? It will be amplified. So you will get very large torque ripples at that frequency, for example. That's one thing that's going to happen here. So you don't want to operate transformers at higher than their voltage level, right? So this is because what? This is because I operated this voltage. Again, this flux is due to the voltage that was placed, right? The voltage and flux are related by this differentiation. So if I put too high of a voltage across the transformer's winding, I get an amplification of this effect. So that's why in a power system you have to control the voltage. Because you want to magnify, you want to, as much as possible, you want to use your magnetic material. For you to use your magnetic material, you want to, as much as possible, have a large d phi, so large changes in flux are required for you to be able to create large high voltage devices. Right? You want these large deviations in flux to be available. So you want to utilize your magnetic material as much as possible and run as close as possible to the knee points. But if you run beyond the knee point, too much beyond the knee point, you end up with these peaky currents. Fine, its excitation current is less than 5% of the transformer's full rated current, but it's there. So you just have to know it's there. So you want to utilize the material, but you cannot push the limits. So that's why you have to control voltage in a power system. You have to make sure, that's why the transformer has taps. You want to make sure you're running the system, the voltage in the system to satisfy the transformer's operation properly as well as the rest of the system properly. Right? So that's something we also didn't consider in the equivalent circuit.
So, sir, you want to stay, like the goal is to stay away from the saturation zone.
Yeah, you want to run as close as possible to the knee, but not too far beyond. Right? So you will find that transformer designers or machine designers, they will always run close to the knee. They will design it such that, because again, this excitation current is small. So as long as you don't surpass the knee too much, then you've utilized your material properly. Then you've built your high voltage transformer. Right? You want to do this, you want to utilize it because you want a high voltage across your windings. Okay, so let's continue. Surge phenomena is something we also don't consider. We will talk about this a little bit later. So anytime you have lightning or transients, mainly due to switching or lightning. Switching meaning let's say you're switching in a capacitor. Remember, capacitor current can change abruptly. Right? Voltage rises across the capacitor, but current changes abruptly. So anytime you connect capacitors in a power system, you have switching transients. Huge current spikes being drawn in the system. And then anytime you have lightning, same thing, huge currents being pushed into the system. Right? So these phenomena, they, again, current being placed or being put on a conducting material is charge, right? On a material. And remember, all our devices, all our power transformers, transmission line, everything has to be protected from, so humans can be close to it and touch it. So everything, all the equipment is typically grounded. So now I have these huge charges that are being placed because of these transient phenomena. And then I have my equipment that is grounded. It's like creating a big capacitor, right? So we will talk more about this effect we don't show here, but any of our power devices have a corresponding equivalent capacitance to them. Right? And they will exist. And we will talk about this a lot when we talk about overhead lines, transmission lines. We will calculate the capacitance for transmission lines. Okay, so now we go to the more important stuff, more interesting stuff. I mean, the previous stuff was interesting, but now we'll go to numbers. Okay, so we'll try to apply everything we were doing now. So before we apply everything we're doing, I will introduce something called per unit notation. Per unit notation is basically normalization of the number system. So I want to be able to sit in a room, have a full power system of Qatar in front of me, and know where there are problems by just looking at numbers, okay? But I cannot be sitting here and memorizing, okay, the transformer in this zone is 480, 120. The transformer in this zone is 66, 130, 66, 33. The transformer in this zone is so-and-so, 11 kilovolts to 480 volts. It's very difficult to do that, right? Because maybe we bought maybe this transformer is 10 kilovolts, it's not 11, right? Maybe this transformer is 33, not 34, or 36, not whatever, right? So, if I normalize numbers, then everything will be close to what? 1, if it's normal, right? So if I'm able to take my full power system and normalize everything in it, then I can look anywhere around the power system and say, okay, this is 0.9, that means there's a problem. This is 0.8, that means there's a problem. I don't care about what the actual voltage is. And I don't need to memorize it. I just need to find a way to normalize the power system. And this is called per unit, the per unit notation. And it's basically a way to express the ratings of equipment and the parameter values in percentage or as a number between 0 and 1. right? So basically, instead of as a percentage, we represent everything as a number between 0 and 1. And we have 4 quantities in electrical power. We have voltage, current, power, and impedance. Do we have anything else? No. Voltage, current, power, and impedance. Really, this is all electrical engineering, Ohm's law, right? And the power dissipation. So given any 2 quantities, we'll be able to find the other 2, right? This is the strategy. So for you to be able to normalize everything to a certain standard system, you should have to agree on certain things. So we will have to agree on, for example, I would say the base power, we will call it the base power. Base power is what you will take the equipment rating and divide it by. So if I tell you the base power is 20 kVA, and you have a 10 kVA transformer, then in per unit, the rating of your transformer or your equipment is the actual value, which is 10 kVA in your case, and what I'm saying is my base, right? So it's like percentage, right? You get, inshallah, 95 out of 100, right? So you get 0.95, right? So my base is 100, your actual value is 95, so 95 divided by 100, right? So we will come up with base values for all these 4 quantities, right? So we will come up with base values for power, base values for voltage, base values for current, and base values for impedance, for every place in the power system, for every zone in the power system. What do you think is going to be the most problematic part about this one, about normalizing the values around the power system? Power, I don't think it's an issue, right? Because base power on the primary side, secondary side of transformer is the same, right? I'm transferring the same amount of power. So power will not be really an issue. Impedance, maybe. The most problematic part will be the voltage, because anytime I have a transformer, I have a significant change in voltage that's happening because of the transformer being in the circuit, right? But it would be very nice to be able to make every transformer look as a simple ideal transformer with a 1-to-1 ratio. How would you do that? If I look on one side of the transformer and say I will have the base voltage on one side of the transformer equal to the rated value of the transformer, the rated value of the transformer's voltage. So what is the per unit value of the voltage on the transformer? So I have a transformer. This is 480, 120. I want to figure out a way to make this look like a 1-to-1 transformer, okay, in per unit, okay? And we said that in per unit, what I will do is I will have to take my actual quantity, which I only have what? We have 4 quantities in electrical engineering: voltage, current, impedance, and power. Power is active, reactive, or apparent power in general, okay? So I have these 4 quantities. Anytime I take my quantity and divide it by a base value, I will get my per unit value, right? This is definition, right? Anytime your actual value divided by some base, you will get your per unit value, right? So how would I make a transformer look like a 1-to-1 transformer? I will have to look at the voltage on this side, which is the actual value. It's 120, right? The actual value is 120 volts. Divided by some base value, and it's going to result in my per unit value, right? What would be a good base value to choose on the secondary side of this transformer? On the secondary side, no, I want this to look like a 1-to-1 transformer. So I will choose 120. If I choose the base value to equal the voltage rating of the transformer, then my per unit value of voltage on this side of the transformer is 1. Right? I still have a transformer, but I'm just saying that if my per unit equivalent circuit of this transformer's secondary side is 1. How about if I choose 480 volts as the base value on the primary, then I also have a per unit voltage on the primary of 1. right? So this way I've taken a transformer and converted it to a one-to-one transformer. What does a one-to-one transformer do? Remember, transformer V1I1 is equal to V2I2, right? So if the V's are equal, what does this mean as well? It also means that the I's are equal. I1 is equal to I2. What does this mean? It means that I can take my one-to-one transformer and make it look like this, right? So this is what we will make the transformer look like. Nothing. We will make it disappear, except for, but this was the ideal transformer, right? We had some impedance. Remember we said that transformer will be resembled by some impedance, X equivalent on the primary side or the secondary side. So we will have some impedance. So impedances, we cannot just throw away, right? We'll have to figure out how to, okay, bring this impedance into the circuit. So we'll go through it slowly, but I just wanted to show you where we're headed here. This is where we're headed, yeah. So let's look at what this the per unit system gives us. So as I said, the per unit system gives us the benefit of being able to play with transformers in our equivalent circuit with minimal effort. And we will see how we will be able to basically eliminate the transformers to a large extent. For the most part, we'll be able to eliminate the transformers. And of course, we'll be able to solve everything using our single-phase equivalent circuits very easily. Since transformers were eliminated, then we just have an impedance in our single-phase equivalent circuit that we need to deal with. Most quantities involved in the per unit calculation are of the order of 1, right? So since everything is normalized, then everything looks like 1. So anytime you see something that's far away from 1, you know that there's a problem, right? Which means that it will help you detect anomalies in the system, etc., etc. So let's do some of the math. So some of the math involved is the following. So in per unit, the per unit notation, the per unit value of any of the 4 quantities that we have is basically the actual value divided by some base value. Actual value divided base value. Actual value divided base value. Same thing for power. And then the power relationship holds as well. So the base power, but there's no base values don't have their magnitudes only. They don't have angles. They are not phasors. Okay, so forget about this V equals S base equals V base times I base conjugate. Forget about the conjugate. Even the textbook, I think they have the conjugate there, right? But base values don't have an angle, right? It's a quantity, right? I'm taking, you have a 1 amp angle 10. Convert that to base values. This is actual. I divide it by base. My base cannot have an angle. If the base has an angle, it will change the angle of the current, right? I cannot have an angle. It's only a magnitude. So base values are only magnitudes. So you will take the actual values, which have magnitudes and angle, divided by base values, which are only magnitudes. Choice of base is what this is all about, actually. So if I choose, I will choose a certain base value for 2 of the quantities. Remember, we have 4 quantities: voltage, current, power, and impedance. If I know 2, I will find the other 2, because everything is related either by V equals Z times Z times I, or S equals V times I, right? Of course, the per unit values have angles, right? The per unit values, per unit quantities are complex, but the base values don't have a magnitude, right? Only the base don't have a magnitude. The per unit, they have magnitude. They have to be. Okay, but anytime. So now I have 2 equations. These 2 equations have 4 unknowns. So if I'm given 2 of the unknowns, I will have 2. So typically, we will always say, okay, I will choose a power base, and I will choose a voltage base in any system. And then after choice of voltage and power bases, I can calculate my current base, since I know my voltage and power base. If I know my voltage base and power base, I should be able to calculate a current base. From a current base and a voltage base, I should be able to calculate my impedance base, right? So now I have a voltage base, impedance base, current base, power base. So I have base quantities for all the 4 physical quantities that we have in a power system. Then you go and convert all impedances to per unit values. All the impedances, all the voltages to per unit values. And we will have to do that every time we see a transformer, right? Because remember what I said was, we will choose 2 and solve for the others. So we will choose a power base. That will not change around the system, right? A power base is going to be consistent. I have a power base of 20 kVA. This will be chosen based on maybe the highest rating of equipment in the system or the average rating of components in the system. It's a number. There's no wrong answer, guys. Okay, there's no wrong base to choose. Okay, there is a base that will give you reasonable intuition, and there is a base that will be useless, right? If I choose a base to be 1000 volts and my transformers are 100 volts, then what is the per unit value of voltage? Actual, which is 100, divided by base, which is 1000, 0.1. It's not very intuitive. I mean, I choose a 1000 volt base, and then I have another transformer that is 1000 volts in the system. Then 1000 volts for that transformer divided by 1000 volt base is 1 per unit. So this transformer is okay, it's healthy, and this transformer is also healthy. But the per unit value here is 0.1, the per unit value here is 1. Does it make sense? No. So I had a wrong choice of base. Right? It was not a good choice of base. It's useless, basically, right? In this case, useless. But every time I see a transformer winding, I will choose a base. Because transformers change the voltage. So every time you see a transformer, you will choose a new base voltage. But the base power is the same, because the rating of the equipment is the same. It does not change in the system. So every time we see a transformer, we will choose a voltage base. We have a constant power base in the system. Then from these two, we go on every zone, every transformer, we have to recalculate the current base, recalculate the impedance base. And then after you have all your base values, convert all your actual values in the circuit to per unit using these equations. And then solve. So how do we do that? I know it's too much talking without numbers is not very nice. So let's do an example. So we have a single phase transformer rated for 20 kVA, 480 volts on the primary, 120 volts on the secondary, 60 hertz. The equivalent leakage impedance of the transformer referred to the 120 volt winding is so and so. This is the equivalent impedance referred to the primary side. The equivalent leakage impedance of the transformer referred to the secondary side. Referred to the 120 volts. Using the transformer ratings as base values. So here they're telling you choose the transformer ratings as base values. What does that mean? It means that I will choose my power base to be 20 kVA, and I will choose my voltage base on the primary to be 480 volts. And I will choose my voltage base on the secondary to be 120 volts. This is what this means. Use transformer ratings as base values. Right? Determine the per unit leakage impedance referred to the winding 2 and referred to winding 1. So, what are they asking for? They're telling us we have a transformer. They're telling us we have a single phase transformer here, and that this winding Z equivalent 2 referred to the secondary side. So I took which means I took all the impedance on my primary side and converted to my secondary side, and I have some Z equivalent on the secondary side. Z equivalent 2 is equal to 0.525 angle blah blah blah, right? So this is my impedance. This is a 480 volts transformer to 120 volts transformer, 60 hertz. And then using transformer ratings as base values, so S base is equal to 20 kVA. V base on the primary side, right? Anytime you see a transformer, you will recalculate your bases. That's the only thing, that's the only trick here. Okay, anytime you see a transformer winding, recalculate the base. We will choose a base on the primary side of the transformer, which is equal to 480 volts. We will choose a base on the secondary side of the transformer, which is equal to 120 volts. Right? So now I have S base, V base. What am I missing from my quantities? I need to calculate Z base, and I need to calculate I base. These are the first two things that I need to do, right? I know that S base equals V base times I base, right? So I have S base, but then I have V base on the primary and V base on the secondary. Which one should I use? I base on the primary will also change versus I base on the secondary. So if you use I base 1, V base 1 here, you will calculate I base 1. If you use V base secondary, you will calculate I base on the secondary side. So now I have my current bases on the primary and secondary, voltage bases on primary and secondary. I'm missing my impedance bases as well. So if you go back to the equations, V base equals to Z base times I base. Same thing, you can use, if you use V base 1, I base 1, you will calculate impedance base on the primary side. V base 2, I base 2, you calculate impedance base on the secondary side. So now I have voltage bases, current bases, impedance bases, and power base on everywhere around on the primary side of the transformer and the secondary side of the transformer.
You have to find them all, or can you find only one base?
You will have to do whatever is required by the problem. So in this case, I don't think you will have to find, I think this case you will have to. So here what they're asking us to do is what? They're giving us an impedance here, Z equivalent 2. They're telling us, okay, using a transformer, determine the per unit leakage impedance referred to winding 2 and referred to winding 1. So this is the impedance referred to winding 2. They want it in per unit value referred to winding 2, kept on winding 2. So what are you going to do? Yeah, exactly. So we would need to calculate Z base 2. So V base 2 is equal to Z base 2, I base 2. So from Z base 2 and Z equivalent, you take Z equivalent, which is an actual value. We divide it by Z base 2, and that is Z per unit on the secondary side, right? And then, so that's my Z per unit on the secondary side. So now they want it also from the primary side. So they want determine the per unit leakage impedance referred to the winding 2 and referred to winding 1. Okay? If I'm going to refer to winding 1, there are two ways to do it, right? You know that if I take any impedance, I can refer to the primary side by multiplying by the turns ratio. After I did this per unit analysis, what does the transformer look like? What is the voltage base on what is the per unit voltage of the transformer on the secondary side? 1. What's the per unit voltage of the transformer on the primary side? 1. So if you take this impedance in per unit on the secondary side, multiply it by 1 squared, it will be the same on the primary side. Right? So if I look at the transformer from this side, same impedance, look at the transformers from this side, I see the same impedance.
But the per unit impedance would be
Per unit, of course. Per unit impedance will be the same. The actual will be different because the base impedance and the primary base impedance secondary are different. Right? So this is not the approach the way they did it in the textbook. I think the textbook, what they did was, okay, I will take my actual value, initial actual value, multiply by the turns ratio squared, which was the 480 divided by the 120. So they will bring you the actual value on the primary side. And then they will, okay, you will calculate the base on the primary side, or use the base on the primary side, divide them by each other, and wow, they're the same. So that's what they're trying to tell you, that they're the same. So what does this mean? If I look from this side of the device, I see an impedance. I look this side of the device, I see the same impedance. What does this mean? If this impedance was 0, I was seeing a short circuit, right? Right? It's basically I'm seeing 0 if I go on this side, see 0 if I go on this side. This means that I can represent the transformer with its series impedance as nothing but a series element in my single-phase equivalent circuit. That's what this exercise means. Right? So I was able to reduce my transformer to a 1-to-1 transformer. 1-to-1 means E on V on V on the primary side, I on the primary side is equal to I and V on the secondary side. This means I can represent a transformer like this. But this transformer has, this is the ideal transformer. This transformer has an impedance now. This impedance has some value. Using per unit, we saw that, okay, I can also, if I look from this side, the impedance is the same as if I look from the other side. Primary and secondary, it looks the same. So if that's the case, then I can basically put the impedance here and say this is my representation of a real transformer in a power system. This is the result of, this is what this exercise is trying to tell you. So let's look at the solution and confirm that. So I'm not going to go through the solution in detail, but if you see here, Z per unit, Z equivalent per unit is 0.729 blah blah blah, right? 0.729 times 78 times 0.13, right? And then from the primary side, same Z. Okay, so that's what they're trying to tell you here, and they did it pretty much the same way that you find you have S base given, V base primary side, V base secondary side. Then you have to calculate the impedance bases, primary and secondary. So Z base equals to V base squared over S base. You calculated the impedance base, or you can first calculate the current base. But here you didn't need to calculate the current base, right? So we calculated the current base. We can calculate the current base. I mean, here they don't. But typically what I like to do is I like to draw the circuit. Anytime I see a transformer, I put a line and calculate all my base values here, all my base values here, all my base values here, and then solve. We will go through an example like that, I think, in next class. I will have to stop here. Next class we'll do a more involved example. So the homework will be mainly around this stuff. Okay, so I will assign it today. I don't think you'll be able to get far enough. I think you will, after next classes, you should be able to do the homework.